All right, remember the circle bounce problem? You're given a circular room, you start a ball, and you bounce off, you stand at -1, 0, and you bounce the ball off, and you're asked what happens to it after this many bounces. Now, more importantly, you're told that n is a very large number, and you're told that all your answers need to be modulo this ugly looking number. And so you're supposed to find the point and write, if the point is r comma s, where r and s are rational numbers, if it's r divided by s is one of the coordinates, then you're supposed to write it as an integer in this form, where k is r times s inverse modulo m. So there's some modulo arithmetic stuff going on here that you have to worry about. So then, where are we? Yeah, so you're asked to find the point, and we talked about this very briefly, saying that what happens to the coordinates as we go through the bounces, and it turns out that the points look exactly like this, except with a plus or minus sign thrown in. Okay? So if we can figure out sine of 2n alpha and cosine of 2n alpha for all values of n, we can get to any number of bounces we want. That's basically what we know.
So what we're trying to find, so n is the number of bounces?
Yeah.
And then we're trying to find the pairs of the coordinates at the
correct.
At the circumference.
Yeah. And the coordinates have to be written in this bizarre form, which is modulo m. Okay. So those are all our challenges. Now, the first challenge, of course, was to figure out what the formula is, and we figured that out. The second was that we had to deal with some very large values of n. And there, instead of going n equals 1, n equals 2, n equals 3, and doing it sequentially, we were going to jump. We were going to go 1, 2, 4, 8, 16, 32, etc. And it turns out if you do this, in 40 steps, I'll get to at least 10 to the 12. And then we also figured out what happens if it's not a power of 2, at least conceptually. Then our next challenge was to keep everything rational, keep the coordinates to be rational. And that's a big challenge because we're writing coordinates in terms of a cosine of some strange angle. How could that be rational? How could we write that in a rational form? It turns out that if your tan alpha is a rational number, a divided by b, then you can write down tan of 2 alpha in a rational form. You can write down tan of 4 alpha in a rational form. And here's the formula to do it. So essentially, you're going to build this table, which will give you the coordinates of the point, or at least the tan values, for every power of 2. All right, and there are only 40 of them, so you can do this quickly. And once you do this, you can find it for any value of n fairly quickly. So this part, I haven't quite made up the slides for you. So all the modulo arithmetic, I think we'll spend another day where we'll go through modulo arithmetic somewhat more carefully. For now, if you have access to some website or a book that explains this, go ahead and read it. Otherwise, we'll delay this for some other time. But that part is somewhat more standard. You're going to see that in many problems, so we have to work it out at some point. We also have to deal with the fact that numbers can be very, very large, which means you can't write it as an integer or a long integer. You have to write it as an array of digits, and you have to do all this arithmetic, modulo arithmetic as an array of digits. And so there's some stuff involved, but they are all somewhat standard. Does this sound reasonable? So this is not an easy problem. There are lots of little pieces, pieces that you need to feel comfortable with. But you need to understand that each of those pieces can be managed. And that's what I was hoping to get to. Is this okay? Questions? What part here might pose challenges for you, you think? let me show you the challenges again. These are what we call as our challenges. Anything here that you think you will not be able to figure out over time? Not too happy about this?
So the part, I understand the powers of 2, so you get P of n, and
Yeah.
P of 2n.
Yeah.
The addition part is the one I'm not understanding.
Right. So for the addition part, think about it this way. If I have, right, so essentially if you look at this table here, right, if you look at this table, what it says is that I can figure out what happens for p of 2 to the 1, p of 2 to the 2, p of 2 to the 3, and 2 to the 4, and so on. So, well, actually, we should go back to this picture here. So for some reason, my mouse is refusing to work, but that's OK. So if you look over here, it says that the polar angles are very well defined. It starts off at pi and then becomes pi minus 2 theta, then it becomes pi minus 4 theta, and so on. If instead of starting at pi, if I start somewhere else, let's say some arbitrary theta, not theta, arbitrary lambda, then the same numbers, so let's say it's something, p of m, let's say is lambda. Doesn't matter. After some number of bounces, you reach this polar angle. What this tells you is that p of m plus 1 is very well defined. In fact, it's going to be lambda minus 2 theta. P of m plus, m plus n, where n is some power of 2, let's say it's 2 to the k, this also is very well defined. So therefore, if I'm adding 2 different powers of 2, all I have to do is to start from that point and then add that up, that's all. Now, I know I'm still not being clear enough. How do I? Right. So let's say that this m is some 2 to the power k1. And let's say that we now want to add a different power of 2, right? So what we are going to end up with is something that looks like this. You're going to get cosine of, when you do the first one, you're going to get 2n alpha, 2 to the, this is going to be 2 to the k1 plus 1, is it? Yeah, 2 to the k1 plus 1 alpha. I'm ignoring the plus or minus sign, so bear with me. And then I am going to get plus an extra 2 to the k2 plus 1 alpha. This is what I'm going to have to deal with. This will be one of the coordinates. And this I can write using my cosine formula as cosine A times cosine B minus or plus sine A times sine B. And each of those has been figured out in a similar fashion. So all I have to do is to plug in those values. Okay? So it's more a matter of adding those angles and computing the cosines. A little more convinced that the pieces come together? Yeah. So essentially, I can add powers of 2 with some little extra work that involves using these formula. So, but yeah, without these formula, we'd be dead. We wouldn't know how to deal with this. You guys still look dazed. Any questions? Anything I can explain? So the trick here is to compute all the powers of 2 and then add them up as necessary. By adding powers of 2, I can get to any intermediate number that I want, which is not a power of 2. So I can compute all the 40 different powers of 2 that I have to deal with, for n being all the way up to 10 to the 12. By combining them in simple ways, I can get to any other number I want. It's like binary, exactly. So you take your n, write it as binary, and you'll know exactly what powers of 2 you have to add up. And these formula will tell you how to combine them. Okay? Then you would have your final point, or actually the final polar angle. And once you have the polar angle, then everything else is somewhat simple. Okay? There may be simpler ways to do this. I don't know. These are the pieces that I figured out by thinking about it. If you come up with a better way to do it, please let me know. Yeah. So then, yeah, we talked a little bit about the challenges. I showed you how to keep it rational by using those formulas, right, for tan 2a, cosine 2a, and sine 2a. And then the modulo arithmetic, I mean, if you don't know this already, at some point we'll go over it more slowly. How many of you know how to do the modulo arithmetic? Okay. we need to learn that well, right? So one of these days we'll go over it. What do you think? Should we stop here and move to a different problem? We don't have all the pieces in our head yet, but soon we will. I just want to convince you that it's a manageable problem. It's not an impossible problem. And anyone who knows a lot of the pieces can put them together, even in a competition. Questions for me? Okay. So the next thing is to go and look at this other competition that you guys worked on, right? Yeah, here there were two problems that Ricky sent me. One was this cubic cycle one, and the other was this polygonal problematic polygon. So let's spend a few minutes with cubic cycle. I'm going to tell you some general things, and then we'll spend a few. Then the rest of the time we'll talk about problematic polygons. So let me please read this. Should I make the font bigger? Yes. I thought you guys were young. Okay, so what's a Hamiltonian cycle? It's a cycle that visits all the vertices. It's no different from the traveling salesperson problem where you have to visit all the cities. The only difference here is that there are no weights for the edges. If there are no weights for the edges, the traveling salesperson tour is the same as the Hamiltonian cycle. Okay? And you're given a graph, and you're asked to, what are you asked to do? Sorry? You just want the count of the number of cycles, of Hamiltonian cycles. Now, the important constraint here that you need to understand is this one here. Where did that go? Yeah, each vertex in G is the endpoint of precisely 3 edges. It turns out that this is the key constraint that you should pay attention to. Okay? Now let's talk about why this is important. Well, first of all, what you need to know is that the Hamiltonian cycle problem is even figuring out whether a graph has a Hamiltonian cycle or not is an NP-complete problem, which means that you should not look for any efficient algorithms. You should simply jump straight to brute force exponential time search, brute force search algorithms. Great, we're stuck with exponential time algorithms, and then you should know that the exponent, because it's an exponential time algorithm, you have to worry about how many vertices there are. The bad news is that you could have up to 50 vertices. This is really bad news. Why? Because 50 factorial, if you're going to try every possible permutation, remember, every Hamiltonian cycle is simply a permutation of the vertices. If you write things in a certain order, if all the edges are there, that will give you a Hamiltonian cycle, and you're supposed to count how many of these Hamiltonian cycles exist. So a very, very simple algorithm is as follows. You take all the vertices, you write down every possible permutation, and check whether that permutation corresponds to a Hamiltonian cycle. So if my cycle is 1, 3, 2, 2, 0, I can check whether each of those edges exist, and I'll be done. That would be one of the counts. So if I write down all the n factorial permutations, I can easily check whether it forms a cycle or not, and then all I have to do is to count the ones that worked. So therefore, if I were to do it this way, the time complexity would be the number of permutations on n numbers. The number of permutations on 50 is 50 factorial, and 50 factorial you should not be dealing with in any, trying to compute this in any way, shape, or form. Or you shouldn't be looking at 50 factorial permutations, because that'll take way too much time. So what do we do? So that means this idea of just looking at all permutations is a bad idea. So cross that off your list. We still have to do exponential brute force search, but we shouldn't be that brutish. We've got to be smarter than that. So the question is, how do we get smarter? So the way you get smarter is because of that constraint, the one that I highlighted there. What it says is that every vertex is adjacent to exactly 3 vertices. So remember, it says exactly 3, right? Precisely 3. It's not less than 3. It's not greater than 3. It's precisely 3. So that helps us because, why would it help us? Sorry? Yeah, but why is it limited? Limited for what? I still have to write down n factorial permutations, I think. N is not a lot lower. N is still the same. It's just that for each vertex, the neighbors are fewer.
Whenever you find one cycle, you can make assumptions about other cycles because you already know the edges that you have to.
Right. That's basically the idea. What we're going to do is we're going to start at some vertex and then look at the possible next steps. Instead of trying to write down all possible permutations, most of which are not going to work out for you. We'll only look at the neighbors and use those as our next thing in the permutation. So for instance, well, this is actually a silly case because everything is a neighbor of everything, so it doesn't really work here. But if you think of a larger graph, let's say there were 10 vertices. So if you draw a graph with 10 vertices, that's 10 vertices. And let's just say I put in how many neighbors does each vertex have? 2. So we've taken care of 2 already. You can only have 1 more. So let's say I connect this to this. Now each vertex has exactly 3 neighbors. So let's give them all numbers. So now if I were to start at 1 and think about all the permutations that can give me a Hamiltonian cycle, what's going to be the next vertex on this Hamiltonian cycle? It can't be anything. It can only be the neighbors of 1, which is either 2, 10, or 5. So that starts to limit your search. And you'll see soon that this makes the problem a little more tractable. And then we have to do a little bit more work. So what we're going to do, by the way, a Hamiltonian cycle must visit every vertex, which means in particular it must visit vertex number 1. I'll make that my special vertex, and I will start my search. I will always start my search there. So let me assume I will only look for permutations that start with 1, because anyway I have to come back here. So I'm going to fix that first vertex, which means I don't have to think about it. So 1 is set. Then the question is what my next vertex is going to be, and I'm going to show it this way. I have 3 choices. So I have 2, 10, or 5. If I go to 2, what are my choices? 3, 6, or 1. Sorry, or 9, yeah. Well, it's not 6, sorry. 3, 9, or 3 or 9 or 1. Obviously, I don't want to go back to 1. So that means there are only 2 choices, 3 or 9. Right? If I were to go to 9, really I would have only two other choices, 8 and 10, and so on and so forth. Now imagine drawing this tree to its completion and doing the search. And you'll see that some of these things will start to cut off. You will have fewer and fewer branches as you go down the tree, and your search will get faster. Without providing any guarantees that it will be not as bad as 2 to the 50. In the worst case, by the way, over here, if you ignore just this first top one, you will see, well, by the way, actually, here is one little trick. If I start at 1, I am going to either end at 10 or 5 and then go back to 1, right? That means I don't have to worry about one of these branches. I only have to worry about 2 of these branches. Does that make sense? You don't agree with me. Actually, I don't agree with me even either.
If it's a cycle, you can go both ways, no? So you only have to worry about 2 branches for 1?
Right. So good. So what I'm going to claim is that I don't have to worry about 5 at all. The reason is when I end this, I'm going to look for endpoints that have either, if I'm taking this branch, I'm only going to look for endpoints that are either 10 or 5, otherwise I'm not going to stop. So, so that means I don't have to consider that branch. In fact, I don't even have to consider 10 because that also is automatic. So that first one, I'll just assume I'm going to go from 1 to 2. Is that correct? No, that's not right. Sorry, that's wrong. Okay, I have to take 2 of these, yeah. If 1 to 5 was a correct branch, then it has to come back either through 2 or 10. So therefore, instead of going this way, I'm going to be looking at it from the other direction. So therefore, I don't have to worry about this. Which means that at every point, I'm only going to have at most 2 branches going out. So except for this top vertex, everything else will have only 2 branches going down, right? Which means it looks like a binary tree. And remember, what is its depth? You can't have any vertex repeated, so it has to be n, which means that this tree is going to have at most 2 to the 50 vertices. Now, 2 to the 50 is already way too much. You don't want to deal with 2 to the 50. However, the good news is that not all the 2 to the 50 are going to be in play. Sooner or later, branches are going to get cut off because when you get to 3, well, not 3. Let's take a different example. Let's say we take 8. When we get to 8, you will have 4 or 7. There will be points where you won't have any other place to go because everything else was traversed at the, in the path that you already come to. So branches will start to chip off. And so you won't have to go and look at all the 2 to the 50. So this is called a smart pruned search, where you constantly check whether you are going over the same things over again. And if you keep track of things properly, then you won't end up with looking at all of the 2 to the 50 possibilities. So even though this tree, by the way, this tree is called the computation tree because these are the choices you have to look at. Even though this is the computation tree, you're not going to go and look at each one of those nodes because not many of them are viable. So essentially, you're going to set this up. Anytime you're at any vertex, you know exactly the vertices on the path that led to here. And so you would know what choices you cannot take. And so therefore, you would quickly chop off your search. You might hit dead end somewhere, and you'll say, OK, I can't go anywhere else from here. And since I haven't covered 50 vertices, I can stop. So you use that to kind of keep track of which ones worked out. Anytime you finish all the way up to 50, you count to 1, and you keep going. So all of this worked out because every vertex has exactly 3 neighbors. Otherwise, your search could get to be too heavy. OK? It is still exponential, by the way. It's just that if you prune things properly, it'll be manageable exponential. The bound cannot. I don't know the right bound, but it's going to be manageable. I think it's 2 to the n over 2 or 2 to the square root n or something like that. I don't remember the bound. And if you look at it that way, even 2 to the n over 2 is 2 to the 25, which is not really that bad. That's only about something like 16 million, and it's manageable. Sorry, 32 million. Yeah. OK. So this is essentially brute force search, but implemented in a way that you're careful and you prune things as soon as you know it's not going to work out. So here you're just going to do a what's called as a depth first search. You will go 1 to 2 to 3 to 4 to 5, and all the things that you come from, they will all be on the stack, so you'll know which ones have already been visited. You can keep track of that, and the moment you have 30 things, as long as you have n things on the stack, and if you can go back to the start point, you can stop and count 1. Otherwise, you backtrack and you continue. So it's your basic exponential backtrack search, brute force search. And we've done this in class. We can go over this again at some point if you want. How am I doing on time? I still have time. Good. Okay, so we have just enough time to talk about this polygonal problem. Can we move on to this? Can we move on to the next problem? You okay with it? Yeah? All right. I'll give you a few minutes to read this, and I will zoom in a bit for you. These are called problematic polygons. Take a look. Here you're given 2 polygons, and then you're asked what? Right. So you're allowed to rotate one of them, I guess. Obviously, you only have to rotate one of them. But you'd like to fit one box into the other bigger box. And you're asked, is this even possible? Okay. And both of these are not convex polygons. They are what are called as simple polygons. So even though the second box is drawn as a nice little rectangle, don't be fooled by it, because the problem says it can be a simple polygon. So that also can be as ugly as the orange one. Okay? Now you're told, what are the constraints? So you're told that the first polygon and the second, both the polygons have up to 100 vertices. So it's not small. Okay? And then you're told the coordinates are integers. That's nice. Thank you. And then you're told that your job is to find, what do you have to report? You have to report an angle such that the distance between any point of a polygon and any edge of the other is at least 10 to the minus 6. So you want some clearance when you fit the other box inside the first box, right? Now, there are a couple of key things to watch out for here, or to note, because those are the key to making this to work. And what are they? What do you think? Corners. What about the corners? Remember, nothing is a rectangle. Both are nasty-looking polygons. No, because you have n. So the first, it says here, simple polygons. So your job is to pack objects with simple polygonal shapes into containers with simple polygonal shapes. Yeah, no rectangles here. No freebies, unfortunately. Well, we could work with rectangles in C, because that's an easier problem and maybe it's more manageable.
Can the polygon, in this example, can the rectangle be completely outside of the outer polygon? Like, can they be in 2 completely separate positions?
Yeah, but you're allowed to move. You're allowed to move, you're allowed to rotate. You can do whatever you want.
Like what I'm saying, let's say one of them is here and the other one is here. Like
Yeah.
there's no intersection. This one is here, the other one is here.
It's only the relative positions that you care about.
But he's asking if there's an edge case, whereas no matter how much you rotate, it's not going to fit inside.
It's not just rotation, there's also translation.
There's translation, so you can move it
Yes. Yes. So let's read that.
Professor,
I'm not right?
I don't see translation.
You don't see translation? Oh, really? Okay, then it's easier, slightly easier. Around the origin. Okay, so all right, so there's a strict origin. Okay, I'm wrong. Okay, yeah. So then, of course, it's possible that the answer is, well, in that case, you would say the answer is impossible. So you don't have to worry about it.
So like if we know, like, yeah, let's try and make the assumption that one is nested inside of the other one.
Uh-huh.
And we'll draw the lines of, like, check if the lines intersect, and I would know, like,
That's right.
if like
That's right.
I'm in a wrong form. So then maybe I could sort of simulate the negation and keep checking if my form is wrong.
Yeah.
I get the right form.
Yeah. But my question was, are there numbers that you have to worry about? Are there things that you should pay attention to?
Rare numbers.
Sorry?
Like rare numbers like the points.
The degree can only be integers.
That's right. This is important. You're not dealing with arbitrary angles. You're only dealing with integer angles. And so, how many different angles are there? 360, that's it. So, at least in your head you should know, okay, because these can only be integer angles, I can check all of these. Whether it works, whether it's manageable or not, is something we'll worry about separately. But that's something you should note immediately, because all that should come straight out of the wording. Minimum integer angle, blah. All right, so if the angles are only integers, they are essentially telling you, you may have to go and try every possible angle. That's really what they're telling you, okay? So these are all hidden codes there that need to register in your head immediately. What else?
I mean, the polygons of 100 is not that big.
Not that big, that's right. So essentially what I'm going to do is I'm going to take one of the polygons, I'm going to rotate it by 1 degree, right? And then I'm going to check whether, as you said, I'm going to check whether any of the edges intersect. That's all I have to do. Right? Really not that difficult. So the first thing I have to do is to figure out how do I take a polygon and rotate it by whatever, x degrees. Is this easy? So here's my origin. Here's some point of the polygon. It doesn't matter what the polygon looks like. It could be something like that. And this is the point I'm looking at. And I am rotating everything with respect to the origin. That's here. And I'm rotating it by some theta. Can I figure out its new position? How do I do this? By using a rotation matrix. There are many ways to do it, but you could do this from first principles if you want, by figuring out what the you draw the triangles and figure out all the so you know this distance, so the distance is going to be the same from the origin because everything is rotating with respect to the origin. And then the angle, here it was something, then here it's going to be that plus theta. So once you get the polar angle, you can figure out the coordinates. So theoretically, we know how to do this, right? You can do it with a rotation matrix quite easily, because you take x, y, you multiply it by a 2 by 2 matrix where there's a cosine theta and a minus sine theta somewhere. Again, figure that in your notes, somewhere you should have this rotation matrix written down. I don't have it in my head. I just go and try and figure this out from first principles, but you can figure this out. Once you do that, you know what its new position is going to be. So you take every point in this polygon, all the 100 points, rotate it by theta, find its new coordinates. That gives you all the edges of that polygon after rotation, and go and compare it against each edge of the former polygon. So 100 edges, rotate them. That takes you about 100 steps. For each of those 100, compare it against each of the other 100, which means you're going to do 100 times 100 computations for whether two line segments intersect. We've done line segment intersection before. You have the code for this. Plug it in, and you're done. Yeah?
What I was thinking is, if the other polygon is nested inside of the bigger polygon,
Yeah.
then you don't have to do any more work.
Yeah, yeah, but that'll come because theta equals 0 will take care of it, so I don't have to worry. But there is some problem. Sometimes you have to figure out what is inside and what is outside, even though they don't intersect. So you have to worry about a few things, but go ahead, finish your question.
Let's say now, like, they're not nested. There will be no intersection.
Yeah,
Plus, one is not nested inside the other. So how do you make this?
right, very good. Yeah, so we have this one other issue where here's the first polygon, here's the second polygon, somewhere here is the origin, and you check even for theta equals 0, nothing has moved, there is no intersection. Are you going to report that you have, for this angle, it all fits perfectly? Obviously, the answer should be no, but how do we distinguish between this and another situation where that polygon sits like this over here and it all perfectly fits? How do you distinguish? Well, that's his question. How do I answer him? What do I tell him? For this, yeah, go ahead.
Okay, I'm not sure if I understand the question. So for this scenario, why does it matter if we're trying all the angles from 0 to 359? If we don't see at any point a successful rotation, the
No.
nested one is the other.
Remember, the algorithm is as follows. I'm going to take every edge in this polygon. I'm going to take every edge in the second polygon, and I'm going to check whether they intersect. Okay? And then I will rotate it by a little bit. I'll do the whole thing over again. Every edge here compared with every edge here. Now, even in this stage, it doesn't intersect. What should I do?
Okay, so Rick and I were talking about this, but isn't it better instead of looking at the edges by looking to see if all the points are within the polygon?
Right, very good. So really for this, you have to add one more test to this, and that involves, if there are no intersections of the edges, then just take one of the vertices. It doesn't matter which one. Okay, take one of the vertices and check whether it's inside the other polygon or outside. And we've done that problem as well in class. How do you solve that problem? So I have a polygon, and I give you a point. The point may be inside or it may be outside. And your job is to tell me whether this arbitrary point that I gave you is inside that polygon or not. Some of you may remember, but the others who weren't in the class, I'm going to look at you to tell me how to do this. Yes.
You can see if there's points like a bigger polygon that have like a x and y value on each side.
For this guy, so let me take that point there. I think this satisfies all the things you just told me. I have x and y on both sides. I can draw you more complicated polygons. Even with your plain eyes, you may not be able to tell me whether my point is in there or not. So, I don't know. I'm going to draw a point here. Is that inside or outside? Not so easy. So this is done using the, well, you guys remember this?
So you can create a line all the way to infinity to the right.
That's right, yeah.
And check the number of intersections with the polygon.
That's right. So there are actually two different ways of doing this. And no, sorry, there's only one way to do this. So you treat this point and you shoot a ray of light in that direction. And check how many times it hits the polygon. And then what do you do? If it's even or odd. If it's odd, it's inside. If it's even, it's outside. Are we good? So is this point inside or outside? This one's outside. And it doesn't matter how complicated it is. Now, how do we do this test? Well, not that difficult, it turns out. I'm going to take, let's say, this edge, and I'm going to compare it against this infinite ray. Essentially, it should be, I know the y coordinate of all the points here, and the x should be greater than this. So I'm going to check if that intersects this, that's all. So if the 2 points have y coordinates above and below this value, I just have to check whether the x coordinate is to the right of it, and I'm done. Very, very simple. Right? So I can do this for every edge. That'll tell me how many times it intersects. And if the number is even, then it's outside. If it's odd, it's inside. So I could just focus on the vertices and work it out, or I could do over here with all the edges, but I do the test for one vertex with that strange test. Okay? Or, as these guys were suggesting, you rotate this by whatever theta, check that every vertex is inside the other polygon. That also is equally reasonable. Instead of checking the edges as being intersecting, check whether every vertex of this polygon is inside. If every vertex is inside, you're never going to have, well, could you still have a problem? Actually, you could. Sorry, that doesn't work. That doesn't work, guys, because here's an example. Sorry. I have this, and I have that. All my vertices are inside, but doesn't work.
I have a question about that one. What if the ray hits the border?
Ray hits the border, yeah. So there are some special cases you have to worry about. It's not so, it turns out it's not that complicated. If it hits the border, if it just touches a vertex, then you count it twice, always. If it hits, if it scrapes an edge, if it goes along an edge, count it as 0. Okay, so yeah, there are some simple things you can do. So just vertices are not going to work for you. You got to work with edges. Okay? So this problem really became a lot easier when you told me I don't have to translate it, because translation is a really, really messy problem. Sorry, yeah.
How would you have gone about solving it?
If you're allowed to translate. I was going to do some hand waving and hoping that you would figure it out. Well, actually, that's not true. I'll give you a few clues. I haven't thought it through, so I can tell you a little bit more. So what we're going to do is take one edge of one of the polygons. So let's say that there's a fixed polygon and there's a polygon that you're rotating and translating, right? So let's assume that this red edge is one of the fixed polygon, is an edge of the fixed polygon. I'm going to take the second polygon, which I'm allowed to rotate and translate, and I'm going to take one of its vertices and I'm going to place it somewhere along this line. And I know the angle with which it has been rotated, so I know how it's going to sit. Right? So now I know its position, I know its angle. I'm going to check whether it sits nicely inside the other polygon or not. Now, of course, I cannot rely on this because this edge here I don't know where it is on that edge. So question is, how do I check every possible location? And in order to do this, there are some tricks here where one possibility is to just take this line segment, chop it into little pieces, and try every possible of those discrete locations. But of course, we are not guaranteed that's going to work. So we have to be a little bit smarter. What we do is when we position this and check whether it intersects that bigger polygon, right? If it doesn't, obviously, if it doesn't intersect the red polygon, we are done. But if it intersects the red polygon, we can figure out how much we need to move this before it clears. Okay, and remember, we are moving it along this edge, either this way or this way. And so we can. There's something called the Minkowski Sum, which helps you to figure out what happens when all we do is translation but no rotation. Okay, and I'm not going to discuss that now, but at some point we can do this separately. It turns out if I stop rotations and only think about translations, I've already rotated it to this angle, but now I'm only trying translations in a way that it touches this edge. And that, it turns out, is a more manageable problem, and there are ways to check whether at any of these positions it hits somewhere else. And the way you do that is essentially you enlarge one of the polygons to see if where it hits the other polygon. I know I'm not being clear, but Minkowski sum requires me to explain a lot more, so it'll have to be some other day where I give you a clean lecture on this. Yeah, I don't know if that makes sense to you. So then you have to do this on every edge, because wherever you put it, if you put it touching one of the edges, you'll be able to fit it in if at all it's possible. So for every edge, you have to try every angle. So it's 100 times 360 times a bunch of extra work, which I'm not telling you right now. Yeah. So yeah, that's a messier geometry problem. I'm so happy they didn't allow translations. Yeah. Can we stop here?